Hello everyone, I'm Yue Wu, an undergraduate student at Peking University. Today I'm going to introduce our recent work, Turboboosting Visible Light Backscatter Communication. This is a joint work with my colleagues, Pu Rui, Ke Nuo, Li Lei, and my advisor, Chen Ren. As the Internet of Things is turning into reality at a quick pace, billions or even trillions of ambient objects are expected to gain Internet access in the near future. Deploying such a massive amount of devices becomes difficult if you need to either wire them to power source or replace battery periodically. Today's wireless technology for IoT consumes tens or hundreds of milliwatts, for example, Bluetooth and LoRa, which hinders the development of devices with long battery life. Recently, backscatter communication has become an active research front, as it effectively offers merely orders of microwatts connectivity to small sensors, and hereby becomes a compelling communication solution candidate in the IoT era. Essentially, instead of active signal transmission, backscatter communication reduces energy consumption by signal reflection. Recent work shows it is possible to hitchhike the information over the ambient signals such as Wi-Fi, FM, and LoRa. However, radio backscatter will bring two potential issues when deployed for indoor IoT scenarios. The first, it interferes with normal daily traffic and exacerbates the spectrum crunch problem. And the second, its leakage through wall yields serious security and privacy concerns in room area networking use cases. Along the line but exploring a different medium, visible light backscatter communication presents an emerging and potentially better solution. It can leverage the existing infrastructures for communication purpose, specifically the dome light. The optical medium intrinsically addresses the RF interference, security, and privacy problems aforementioned. Like most backscatter systems, VLBC systems consist of many tool parts, called reader and tag. To establish a bidirectional communication link, reader first sends downlink data to tag with modulated light. We define this reader-to-tag link as downlink. The tag demodulates downlink data and prepares for the response. At the meanwhile, reader sends carrier signal and listens for response. The tag began replying by selectively reflects light with liquid crystal modulator, which is called a uplink. The final step is that reader receives the reflected light signal and demodulates uplink data. The downlink can easily achieve hundreds of kilobits per second because the photodiode receiver and LED transmitter can reach 1 GHz and 10 MHz respectively. In this case, the downlink throughput is mainly limited by power consumption design. The uplink, on the other hand, only reaches sub-kilobits per second data rate because of the slow LCM transmitter. You can think of a high-end game monitor that has 240 Hz refreshing rate, and that's approximately the speed limit of liquid crystal modulator. We come to a conclusion that the slow response of LCM as uplink transmitter is the bottleneck of VLBC. If we apply square wave driven signal to the LCD, it reaches stable states with low frequency. But with higher and higher driven frequency, the response shrinks to only 4% of the total amplitude with 1 kHz. Thus, traditional OK deteriorates quickly above 250 bits per second, which is the 125 Hz driven source here. To improve the data rate given LCM slow response, our solution includes two core technologies called DSM and QAM. Delayed superimposed modulation improves data rate in a single channel by arranging multiple LCM pixels. Polarization-based quadrature amplitude modulation explores additional channels by exploiting the optical properties of LCM. The figure below demonstrates the signal in DSM view and QAM view, which can work in a complementary way. In order to understand how DSM and QAM works, we need to dig into the physical principle of liquid crystal modulator. LCM can selectively reflect 0° or 90° polarized light, and because of the internal competing forces, the charging edge is 10 times faster than discharging edge. Let's consider the first attribute. How can we explore more channels with it? If we use a liquid crystal modulator with 0° polarizer, called a ILCM. The received signals are shown here. Despite the charging and discharging transition, there are two stable states. The same for a LCM with 45-degree polarizer, called a QLCM. Given the fact that light intensity is linearly superimposed, if we use both ILCM and QLCM to send 2 bits information, we can get 4 stable states in the received waveform. Those stable states form a constellation plane of in-phase and quadrature channel. Furthermore, if we use binary divided pixel error ratio for ILCM and QLCM, it forms a higher order constellation. In real-world deployment, an angular misalignment between reader and tag is very common. We find that a physical rotation of theta reflects 2 times theta in the constellation plane. This is our final design of PQAM. It explores 2 independent channels for parallel transmission, while at the same time it tolerates angular misalignment without performance loss. We define the number of points in the constellation as PQAM order P, and PQAM improves data rate by log P. Let's go back to the attributes of liquid crystal modulator. We then look at the second attribute. Charging edge is 10 times faster than discharging edge. The basic idea is that we give enough time for LCM to go back to its normal state so that it behaves the same every time. While each LCM has limited throughput, DSM improves data rate by overlapping the discharging edge and charging edge. The received signal behaves like this. You can distinguish different code words by the ascending edges at those right points. This is our final design of DSM. It interleaves multiple LCMs and improves data rate by 1 divided by t, totally eliminating the effect of slow edge. It's quite straightforward to combine DSM and PQAM. We send PQAM symbol at each DSM slot. To give you a brief illustration, here is our tag hardware design that sends 8-order DSM and 16-order PQAM signal. You can see that each pixel returns to its normal state before trying to send the next symbol. Next, we go to the receiver design. It has 3 parts. Preamble design helps to detect packets and do frame alignment as usual, while it does one more thing to correct the PQAM rotation. Demodulation design includes a optimized decision feedback equalizer for near optimal performance. Channel training in the end handles subchannel heterogeneity from different LCMs to assist the demodulation. Given the received signal, we find those candidates that best emulates the received signal. By keeping the candidates to at most 16, the computational cost is bounded. Keep doing this for the rest of the packet, the demodulation result is the best one among all candidates. The modulation process needs accurate model of LCM to reconstruct the expected received signal, but we find several defects of the simplified post-response model. These defects lead to the failure of our early experiment, and thus we design a channel training process that takes them into account. The channel training design is composed of 2 parts, an offline channel training that takes hours to collect, which results in a set of reference spaces, and an online channel training solving the coefficients of those reference spaces and reconstructing responses for individual LCMs. We developed the customized reader and tag hardware to verify our design. The working range is 7.5 meter for 8 kilobits per second and 10.5 meter for 4 kilobits per second, which satisfies most indoor IoT scenarios. Thanks to the carrier signal design, our system behaves consistently regardless of the ambient light condition. There are 2 kinds of angular misalignment, as illustrated here. PQAM tolerates raw angular misalignment theoretically, which is verified in our experiment. For the yaw angular misalignment, our system tolerates at least plus-minus 40-degree misalignment. In conclusion, we revisit material and optical properties of liquid crystal modulator. Based on that, we propose 2 novel modulation schemes that exploit LCM's asymmetric response and polarization manipulation capability. We pushed the data rate of visible light backscatter communication by 8 times in real-world experiments and 32 times in emulation.
Hey, thanks for the great talk, Hugh. So for the attendees, feel free to ask questions on Slack or on Zoom. And as the questions come in, I'll just start with a question of my own. So you talked about VLC backscatter, and there is a couple of other papers in this session on RF backscatter. And as you know that both of these have their own pros and cons. So are there particular applications that you think VLC backscatter is more suited for than RF backscatter and vice versa? Like how would you draw the line between the two? Like which one do you prefer for which application?
I think an indoor IoT scenario is especially this technology is especially useful because you have multiple users in a small area, and then you want a wireless link that is not conflicting each other. So maybe just the indoor small sensors and the sensor network maybe.
Makes sense. So there is another question coming in from Shaoqi on Slack. So the question is, what is the power overhead for this approach? Because there's multiple liquid crystal panels, and presumably it will cost more power as well because of the multiple liquid crystal panels.
Yeah, so the power overhead comes from the higher driven frequency. So the power consumption is proportional to the area of LCM. So if we use the technology of DSM and PQAM, we divided the single LCM to multiple small pixels so that the power consumption is not increasing. What does increasing is the driven frequency of each LCM pixel, which is fixed at 250 Hertz in our experiment. So that there is theoretically no power overhead, except for the, for example, the computational overhead that is very small. Yeah. Thank you.
That's cool. So as the other people typing questions on Slack, but in the meanwhile, I can ask you one. So the question is that the size of your tag, it is like about 0.5 meter, right? And that's kind of a big size. So what happens if it is like it interferes with shadows from people moving around, and if there's a lot of people who cover the tag, will that interfere with the normal operation, or is that not a problem at all?
Yeah, if there's someone in the middle of this link and there is an obstacle, this communication link won't work, of course, because this is visible light.
Yeah.
And in our experiment, there is some people walking around, walking bypass, and there is no significant deterioration in the performance.
Mm-hmm. And okay, so there is just one more question before we move to the next talk. So the question is, the reader is custom designed for VLC backscatter, or will it also work for other visible light communication devices?
Oh, okay. Thanks for the question. Our custom designed devices is only designed for the experimental usage, but its technology is a very simple, the visible light communication. Yeah, it does not have, yeah.
Makes sense. Thanks, Eve, for the question, and thanks you for answering all these questions. There are more questions on Slack, so I'll encourage you to look at the Slack discussion and carry that on.
One question is, what application do you think visible light backscatter is most suitable?
Hi. Am I audible?
What application do you think visible light backscatter is better than, for example, Wi-Fi backscatter?
Yes, I think the one potential application of visible light backscatter is in indoor IoT scenarios, because the visible light propagation is a strict line of sight propagation and has have a strict boundary of the area of control, and therefore it can better reuse the spectrum resources in a a space constrained area than in, for example, the wireless, because it may cause more interference in this than visible light.
Thank you. And another question is, visible light can be blocked by obstacles. How do you avoid blocking when you backscatter?
We think this is two sides of the sword. So you want less interference, and you must face the property of the line of sight propagation. But I think people in other area and research have reached measures to deal with this line of sight propagation property, because visible light communication is to at least the visible light backscatter is to be integrated with a lighting infrastructure. And since the lights are usually on the roof, and the coverage is therefore maximized, and people, the user also can easily adjust the tags if it doesn't work, because the light is visible to the users. Yes.